Thanks everyone for joining us. I'm Christine Ragantine. I'm the communications lead for the ADS for Rural America project. Just a reminder to put your questions at any time during the webinar into the Q&A, and we'll answer those at the end. So we're going to start off with Omar Ahmad, our project manager. Go ahead, Omar.
Thank you, Christine, and welcome everyone. Thank you for joining us today. So today's webinar is about things that we've learned that we want to share about testing automated vehicles on rural roadways in Iowa. But I just want to take a very brief moment to tell you about the project itself. So this project is called ADS for Rural America, and it was funded by the US DOT under the US Demonstration Grant Program. And we received funding for the project about 3 years ago, and since then, we have put a vehicle, a transit vehicle that's been outfitted with sensors and software on a 47-mile rural route through roadways in eastern Iowa. This webinar is the 5th in a series of webinars. And so we've already had webinars on the safety management plan that we developed for this demonstration project. We've had a webinar on the vehicle itself and the hardware and the software that makes that vehicle work under automation. We've had a webinar on the participant and safety driver experience. So on this vehicle, we had riders and that we recruited from the communities that we drive through to ride in the vehicle and to share with us their thoughts on trust and perception of their experience. And then we've had a webinar on the data portal. And so the main output of this project is a publicly available data set. And this data set is available now through the data portal. And you can get to the data portal and you can get to the links for all of these webinars on our website. And we've pasted the URL for it at the top of this page. So today's webinar is about lessons learned. And we are going to share with you nine lessons. There were many more, but in the interest of time, we limited it to 9. And so I'm going to turn it over here to my colleague, Steve Cable, that's going to start us off by talking a little bit about sensor range on rural roadways. Steve.
Thank you, Omar. So before we get into talking about everything, I wanted to mention kind of the automation platform that was chosen for this project is Baidu Apollo. Our Apollo platform generally utilized 2 sources for navigating the physical world. There was the HD map, which you use for localization and positioning, and a suite of connected sensors that were used for detecting obstacles populating that world. So for our vehicle, our transit, that suite included things like cameras for detecting traffic signals, multiple LiDAR units, and 2 radar units. But for the most part, Apollo relies heavily, if not mainly, on that LiDAR data to detect and classify obstacles in the world. And it's that reliance and the limitations of those sensors that occasionally produced unwanted behaviors during a drive. So one of the first takeaways we wanted to delve into was a repeat issue that we saw over the course of the entire project. It was this intersection between a county road and a state highway. So planning-wise, our vehicle would head south on that county road, which is headed towards the top of the picture you see here. It would stop at a signed intersection and then turn left across traffic to head east towards the casino in Riverside. The cross traffic speed limit was 55 miles per hour, and they did not have to stop at the intersection. So it created kind of a interesting interaction. And then complicating all of this, the turn wasn't a clean perpendicular turn. We were making a turn that was about 110 degrees off of the heading, which made it kind of an awkward angle for that fused LiDAR point cloud to see obstacles coming from the left-hand side. And so in practice, there were quite a few times where the vehicle had to be taken out of automation to safely make this turn manually. So Omar, if you could go ahead one slide. So before we start playing here, I want to kind of introduce everybody to this layout because you'll see it over and over again throughout the course of this webinar. This is a playback of a part of a drive. On the left-hand side, you see camera views. The top one is out of the front of the transit. The bottom one is out of the rear. And then on the right-hand side, there's all sorts of telemetry from the vehicle, including things like you've got the current speed, you've got, if it's in automation, what speed it's trying to travel at. The big things to note here are at the top over here on the right-hand side, you have this blue bar that says Auto Transit Active. That's showing you, along with this icon here, that the vehicle is under automation at this point. It's not being driven manually. Conversely, if it's manual, that bar will change gray and let you know that it's being driven manually. There's also other sorts of telemetry, again, showing braking and acceleration, as well as steering wheel position, and also a map down here at the bottom. So Omar, if you want to go ahead and start playing. This is, again, traveling south on that road, on that county road, towards this stop here at the intersection. So if you want to pause again here, Omar. So now I've overlaid a top-down view on the right-hand side of what the LiDAR, the fused LiDAR point cloud is seeing at this point. So you see kind of that this area here would be the transit, would be our own ship vehicle as we travel down towards this intersection here. Omar, if you want to go ahead and keep playing for a little bit, and then we'll pause right about here. So one thing that I wanted to point out, and it's kind of a what we saw with LiDAR perception, is you end up getting things called you end up getting shadowing effect from objects. Like here is I believe it's one of the stop signs here, and what that does is cause this shadow off of the back from behind to behind it, that obstacle. And so it's areas like these where the LiDAR is in effect kind of blind to what's happening behind it. So Omar, if you could go ahead and continue playing again. So pause one more time here. Now here I've put in another view of that same LiDAR point cloud, but again, now we're looking towards the vehicle as it comes, and kind of off from the side, looking from the southwest at the transit as it's coming to a stop. So again, you see these rays here, here, there's one here, and then especially the big one to pay attention to is this shadow that we get here. And this one is particularly problematic because it's looking down. It's corresponding to this shadow that you're seeing here. Now that's problematic here because of the fact that all of the westbound traffic that's coming off of this road is essentially driving down this blind spot. So the way that perception works in Apollo is that it's taking a look at the history of objects as they move in the world around you. So by effectively being in a blind spot, the system doesn't know that a car's oncoming. Omar, if you want to go ahead and play the video, you'll see vehicles kind of coming down this from this area and now just showing up right there. And it, again, doesn't give the automation software time enough to react to those objects. So therefore, the vehicle thinks that it's safe to travel on the road even though there's oncoming traffic. So as we play here, you'll see the safety driver actually you'll see the safety driver take it out of automation as we go through the as we go through the intersection. It's in manual, and then the safety driver actually re-engages automation after the fact, after we've safely made when they were assured that there was no oncoming traffic. So that's kind of, again, something that we saw at high-speed intersections with high-speed differential. This sort of an effect really was kind of amplified. And so we saw there were some times that it took the intersection okay, but it was normally in situations where there was light traffic around it. So Omar, if you want to go ahead a slide, we can kind of talk about the inverse of this problem where it wasn't seeing something that was there. The inverse is where it would the LiDAR would potentially pick up an object that was not something that it needed to stop for. So in this particular takeaway, we're taking a look at dust clouds or other particulate matter. So here's a screenshot. It's a still frame from Drive that saw in the top left here, you see a car driving ahead of the transit. It's driving on a gravel road. During the summer, the gravel gets dry, and thus there's lots of dust and other particulate that's kind of kicked up in the air. From the LiDAR's point of view, it sees that somewhat diffuse cloud as a obstruction, basically, and therefore will actually instruct the vehicle to brake because it thinks that there's an object there that it needs to stop for. Now, once the cloud dispersed, the automation would pick back up and keep driving, but it would stop for these sorts of things that, again, a normal human driver wouldn't necessarily stop for. So Omar, if you could go to the next, and we'll just kind of let it play here. Now, in this situation, we're driving on a blacktop road. And Omar, if you could pause kind of around the truck or the tractor here. So on the opposing lane shoulder, there's a tractor with a trailer attached. Now, again, it's not on the road, it's driving on the shoulder. And so the shoulder, again, has lots of loose gravel in the same way a gravel road would. So what happens essentially as we drive by, there's also a crosswind that's blowing. That dust gets kicked up, gets recognized by the LiDAR as a obstruction. And as we drive here, you'll see the vehicle actually react to that and try to do a little bit evasive maneuver there. So again, we didn't see it very often, but it was something that was repeatable. And when there was particulate like dust clouds from gravel road, or we also saw it with sprinkler systems, any sort of like airborne particulate, it was reflective enough that the LiDAR units caught it as an obstruction that needed to be stopped for or maneuvered around. So with that, I'll actually pass over to my colleague Alec Lavelle, who will speak a little bit more about another object detection that we saw during the drives.
Yeah, thank you, Steve. So kind of following along those same lines, this first lessons learned that I'm talking about is pedestrian detection, where we'll kind of see that difference between what a human driver might be perceiving or noticing versus what the transit can perceive and pick up. So if Omar, if you could hit play for me, please. So in the top left, you'll see the front camera view again. If you want to hit pause, you will see those two pedestrians that are walking along the sidewalk towards the intersection. Now, it doesn't show it yet. The transit has just come to a complete stop at the stop sign, but it does want to, the route goes and makes a right turn here. So it would be crossing the path of these pedestrians. As you can see in the Apollo view, they are not picked up yet at all. It has not seen them. And right now the blue planning line has come up. So it believes the intersection is clear and will continue through making that right turn. Hit play again, please. So as the pedestrians get closer to the intersection, you notice they start getting picked up slowly, having the transit LiDAR having issues between them and other objects around them, that they begin popping up yellow and blue. Right about there is good. So here you'll actually see those pedestrians are classified as a blue object in the bottom left Apollo view. So Apollo not only detects objects, but then classifies them. So the green objects you see around are vehicles. Yellow is designated for pedestrians actually, and blue is designated for bicyclists. So as you can see here, we sometimes have issues with perception in pairs of pedestrians or groups of people where it will pick them up as a bicyclist Or as you can see here, a couple frames later, it sees it as a bicyclist and a separate pedestrian. So the detection categorization is very helpful, but it can have issues at times. Now, if we could go back just a couple frames, if possible, you can see, yes, right here. So even though it's classified as a bicycle, it still believes those pedestrians are actually planning to cross the path of the transit here, as you can see by the blue dotted line. That's showing its predicted line of travel for that object. Now, clearly, it is crossing the transit's path right now, but the transit doesn't have any of those blue or sorry, purple or red stop or yield gates up, meaning it has not actually reacted yet to those pedestrians. So as you'll see, as the video continues on, they continue towards the intersection while the transit continues through the intersection. This can be caused by a number of things, along with that kind of the late detection and difficulty categorizing them and their detected plan of travel. That, along with minor latencies in the autonomous software itself, caused a point where even here you can see a frame where the transit thinks it should slow down, but next frame that's gone and nothing actually happens. So you get these times where it did pick them up, it does see them, but it didn't necessarily respond in the appropriate manner. Even though, as we've kind of talked about before, as a human driver, if you're pulling up and you see somebody entering the crosswalk in front of you, you're going to pause, you're going to wait and let them go on, even if, you know, as they're approaching. Whereas the transit, if it doesn't pick them up as soon as humans can, like we can see it now. And because of the different detection issues and stuff like that that can arise, it doesn't always react in the most appropriate manner. And with that, we can go on to the next slide, please. So that last video we were watching was circling the town square of Kelowna. This video and the next slide will be exiting the town of Kelowna on the highway towards a four-way stop. So again, this has a lot to do with human perception, human behavior between the transit and the vehicles around them, and the differences between an early and a late stage or late phase of our study. So as you can read by the title, this video is an early phase of our study, an earlier portion of how the automation worked. And as you can see, as we're approaching the intersection here, we have our red stop gates up and everything. The transit is recognizing the other vehicles around us and the stop sign. And we have started to slow down, as you can see by the brake pedal and the lower speed limit now. So you get play, please, Omar. The thing you'll notice, though, is instead of approaching the stop sign as a quote unquote human normally would, the transit slows down to a very low rate of speed and then continues to creep towards that stop sign. So here you can see it kind of slowing down at a regular rate, but then that rate severely decreases and then it sits at 1 to 2 miles an hour and just continues to creep towards closer and closer towards the actual physical stop line. Now, the issue with this is, you know, most humans, especially in these rural communities, it's all about flow of traffic with these four-way stops. You get up to the stop sign, you see the other vehicles or people around you, and you continue with the flow of traffic. The issue here being, since the transit is approaching this four-way at such a low rate of speed, where it can nearly be perceived as stopped, it creates a lot of confusion with the surrounding vehicles and other motorists on the highway. So in these types of situations, we get a lot of people that don't know if we've stopped, if we're about to go, if we've started moving, and it can cause a lot of confusion and traffic backups in these kind of intersections when the transit doesn't actually get up there, come to a stop, and then continue forward. If we want to move on to the next slide, please. So this is, again, the same view, the same intersection we're heading towards, but later in a later phase of the study where we've worked with the automation software a bit in handling these situations and perceiving the vehicles around us. So we're approaching the intersection again, starting to slow down at that same kind of normal speed, but this time, instead of getting way down to a slow speed and creeping, we're now approaching at a much more appropriate or quote unquote human style of driving, where we get up to that stop sign at a much quicker rate. So we're able to come to a stop and actually perceive the vehicles around us the same-ish way a human would. Now, what's interesting about this video as well, if you want to hit pause right now, is, as you can see, our planning line has us coming up to the stop sign in the bottom left there. And then the transit will not proceed through the intersection until it has come to that complete stop. That's why that creep was an issue. And then here you see us come to a complete stop. And we want to get to, yes. So the transit will come to a complete stop. But as you can see, we also have this big utility truck that's pulling up to the stop sign or the four-way intersection at the same time as us. Now, before, this could have caused a lot of issues had we been creeping up to the stop sign and not, causing confusion between us and the other motorist. But since we approached at a more normal rate of speed, you can see as we play the video, the transit will pick up that vehicle while also wanting to continue through the intersection with its planning line. So as we can see here, we have the blue, red, or the purple, red stop yield gates for these two vehicles. And if you could play again, please. Well, so as that utility truck moves through the intersection, we'll see the blue planning line of the transit actually show up, meaning it's wanting to move forward. However, in this situation, we get, again, that purple yield sign or yield gate. So this is a situation in which the transit wants to move forward, believes the intersection was clear, but now is classifying and has picked up that utility truck. So it is yielding until that utility truck can give it the right of way and get it through the intersection at a much more normal and better flow of traffic rate. And with that, I will turn it over to my colleague, Sherry Rowe.
Thanks, Alec. I'm going to go ahead and talk about our fifth takeaway, which is our encounters with various farm equipment. We had plenty of opportunities throughout the project. I'm going to just talk briefly about one here. On the screen, you can see an encounter with the high clearance sprayer. This is a unique size and shape. It's wide enough that it's crossing the shoulder boundary and extends almost all the way over to the center boundary. Now, the question here is the automation going to be able to detect and identify this sprayer correctly? I know I was a safety driver during this particular encounter, and I know I was thinking to myself, I don't know what's going to happen. So Omar, why don't you play it and we'll find out. So we'll see here that the automation was able to identify the sprayer as a vehicle, and it decreased its speed down to about 30, and we're following at a safe distance. Now, the current state of the automation on our particular vehicle doesn't allow it to leave our lane of travel to be able to pass. So we will sit behind this vehicle until it is no longer in front of us. Now, that necessarily isn't a huge deal for us since we're just traveling along, but it could be a concern for the traffic around us. People can get irritated. A vehicle queue can extend for many cars. People might decide they need to pass from 5 or 6 cars back. Now, this is just one encounter, and we were able to stay in automation, but this isn't always the case. Every encounter is very different. There are different types of farm equipment, some big, some small, some may be pulling implements that may cause issues for it to be identified. There are different types of roads. This is a paved road. A gravel road might be very different. How are the vehicles traveling on the road? This one's taken up the whole lane. What happens if they're just on the shoulder? What if they're just barely on the road? Those are all things that need to be considered. It's important that the A/B testing on rural roadways consider all these various scenarios. Next slide, please. So the sixth takeaway kind of builds upon the farm equipment in that it's encounters with horses and buggies. Now, we encountered these in town, on our highways, and on our gravel road. This particular video is going to show a horse and buggy on the right shoulder. And as you can see as we approach it that the automation does pick up the horse and buggy on the right shoulder. And go ahead, pause. You can see that it is classifying it as a vehicle. And since the vehicle's on the shoulder, and we can see the path of the vehicle really isn't going to come into our lane of travel, the automation makes the decision that it can just continue driving. We're going to continue driving. We're not going to slow down. There's going to be no steering adjustment whatsoever. Now this behavior works, but a human driver wouldn't approach this situation that way. A human driver knows that's a horse and buggy and not a vehicle. A human driver understands that that horse could get spooked. The human driver also understands there's people riding on that horse and buggy and may appreciate a little bit of leeway. So a human driver might slow down a little bit, may steer towards the center line, maybe even cross it if there's no traffic coming. One thing I like to point out is that this is a particularly wide shoulder. It's paved. That's very common on our route because there is a high number of horse and buggies traveling, lots of farm equipment traveling. Now, if the shoulder is gravel, or if it's gravel, as Steve mentioned earlier, it might kick up that dust, which is going to impact the automation's ability to keep driving. If they're slower and they have to drive on the road, we're going to encounter some of the similar issues that we did with the farm equipment, where the automation could be following for miles, queue of vehicles getting backed up. So that's just the amount of things that the automation needs to consider when driving on rural roads and horse and buggies. With that, I am going to pass it over to Cher Carney to discuss takeaway number 7.
Thanks, Sherry. So our vehicle uses an HD map to travel along our 47-mile route. And it drives the route according to the different speed limits that are associated with a particular roadway. And most of the time that's just fine. But there are situations in which a typical driver would reduce their speed below the posted speed limit. And one of these situations is when environmental conditions, such as hard rain or snow or ice, impact the roadway surface. We have a sensor on our transit that collects surface temperature. It can calculate the coefficient of friction, but it's not able to process this information and use it to modify the vehicle's speed in any way. So the transit will continue to drive at the posted speed regardless of these environmental conditions, which can be an issue. Changes in road geometry also impact the driver's choice of speed. So in this video, you see the vehicle driving on the blacktop portion of the route. The speed limit on this road is 55 miles per hour. We felt like that was a little bit too fast, and so we lowered the speed to 50 miles per hour. And again, for most of the roadway, this was fine. However, there are a couple of hills on this road where you can't see if there was someone coming from the other direction. And there are also some curves that were fairly tight. So in both of these cases, a typical driver would likely slow down, but the transit did not, which is why you can see in this video here that the safety driver took over from the automation at those locations. In later phases of the project, artificial speed limits were placed in the map to slow the vehicle, and this helped to increase the comfort for both the safety drivers and the passengers in the vehicle. And with that, I'm going to turn it over to Steve Cable.
Thanks, Cher. So one of the other things that we would like to talk about today is, so part of the project dealt with a V2V implementation. And so for this, we actually implemented as a school bus. We actually, because the logistics of getting an actual school bus were kind of ended up being a little onerous, we actually integrated our software into another vehicle. So it's this Camry you're seeing here circled on the slide. So that vehicle and the transit used a cellular V2V system to let both vehicles know the state of each other as they were in real time as they were driving. So for the school bus, it was telling the transit its position, its speed, And then also other telemetry from it, such as a lighting state. So you'll see the blinking light on top of the Camry. That is the stand-in for what would be the swing arm, the swing stop arm on the school bus. So the transit knew when that lighting was in effect and whether it was in an amber or a red state. So here, when it was in good working order, you'll see the transit drive up. It knows before the actual vehicle is detected that there is a stopped school bus in its path. It will wait for the lighting to actually stop, for the blinking to actually stop on the Camry, which kind of lets you know that the swing arm is pulled back in. And then if you want to keep playing, when that lighting is extinguished, you'll see that then the transit knows that it's safe to drive and can continue past. But otherwise, we'll give a good stopping distance to that stopped school bus. Now, this was all done via cellular system, and we did a lot of the testing out in this area that was very rural. So the cellular signal was not always the best at all times. And so while this was a successful run with V2V, we did have some unsuccessful ones with dealing with loss of cellular signals. So Omar, if you want to go ahead one slide, we'll take a look at a unsuccessful encounter. So this is the same road, slightly different in the way that the school bus is now in front of us in our lane. In this situation, the bus drove into, it had, everything was working great, and fired up its lights. But at some point along this line, the Camry actually lost cellular signal. So the transit just knows its last known position and state, which is that its lights are on and it's stopped. So what will happen is the lights go off on the transit or on the Camry, and it starts driving away. At this point, that stop gate should have gone away for the transit to keep driving. But again, it doesn't know, its V2V system still thinks that it's sitting there and still has its lighting active. So you see going to the safety driver putting it into manual, driving through that stop gate manually. And then once on the other side, they can actually re-engage automation and continue driving. So that happens right about now, I believe. But again, so it was one of those situations where when the system worked, it worked as kind of planned. But because of some of the limitations of these really rural areas, the cellular signal for doing a V2V system with cellular technologies doesn't necessarily always work, and as you can see here, not working leads to either stalled traffic or would require the use of the safety driver to manually get through. So I will now pass it over to my colleague Greg Wagner, who will speak a little bit to more kind of issues on the gravel road section.
Thanks, Steve. Yeah, so again, here's that same gravel road, Kansas Avenue. We travel about 1.7 miles of this roadway in gravel. So here we're going to just play completely through, and then we'll back up and pause at some key moments. So here, our HD map was edited, so the center line of our lane of travel was shifted about 18 inches left. So we travel closer to the center line, which is more natural as a human driver. And you can see that by in the lower left, the dream view, by the thick green band is touching the center line actually, instead of actually in the kind of the middle upper lane. If we jump ahead here to the 21-second point, we can see just before the disengagement, the roadway is actually slightly narrower here on the bridge. There's a bridge that goes over a small creek here. You can see the sprayer is actually parked partially off the road and is yielding right away here. But the sprayer is still quite wide and is taken close to the center of the road. At this point, the OEM forward collision warning was activated, and that prompted our safety driver to disengage automation to and take over and drive around the sprayer manually. Many of our rural bridges on roads like this are potentially limited to weight by weight. Like one vehicle at a time. So therefore, one of the vehicles must yield the right of way, and in this case, the sprayer stopped for us. If we go jump ahead a little bit here, you can see here now in the lower left of the dream view, the sprayer is actually identified as 2 obstacles by Apollo. You can see that by the text is kind of overwritten two IDs of the showing up 2 different speeds and the speed distance from our Ego vehicle. So encounters like this of non-typical vehicles are fairly common in rural areas and may not be easily detected by the software. And if we jump ahead till we take over in manual now, and now we actually go past the transit or past the sprayer, I'm sorry. You'll notice the safety driver will actually drive over, and before they get adjusted here, they are position themselves actually naturally beyond the center line of the road, which is just like we talked about, more natural as a human driving in the middle of the road and then sliding to the nudging to the right for when meeting other vehicles or other obstacles. So ideally our automation would have nudged the transit to the right sooner, but that was not possible in this case. So the takeaway here is that AV testing on rural roads, you must consider scenarios like with gravel roads and non-typical vehicles. So with that, I'll hand it back to Omar, and we can kind of summarize some of these takeaways.
Thank you, Greg. So, so in this webinar, we've given you 9 examples of lessons learned and things that we've seen when we did our testing on rural roadways in Iowa. And we were using one specific vehicle with one specific software, but we believe that the lessons that we've learned are likely going to be applicable to most types of ADS vehicles and most types of automation software. Our experience has shown us that there's a lot of similarities between the automation software, and no one manufacturer or software maker has figured out, that magic formula to make it all work. They all have their own limitations. So we definitely want to give time to address your questions. But before we get to that, I just wanted to quickly reiterate that there is a website that you can go to, and the URL for that is right here. And at this website, you can learn all about the project. You can get more details on the background of the project. You can go to you have links to the webinars. You can sign up for our newsletter, and you can also access the data portal that contains the publicly available data set that is the main output from this project. And then one more thing before we get to the questions is that I want to acknowledge that the funding for this project came from the U.S. Department of Transportation under the U.S. Demonstration Grant Program. We had a ton of support from the Iowa DOT, and we had 2 incredible technology partners in Hexagon and Autonomous Stuff. They are the ones that built the vehicle, installed the sensors on it, and managed a lot of the automation software details. And then Madley Communication did the HD map and continued to update the map and insert markers for us throughout the entire 6 phases of the project. So we're ready for your questions now. Christine.
Okay, so anytime anyone has any questions, go ahead and add them to the Q&A. I'll start with a few that we've already received. This first one is in regards to where Alec was talking about the 4-way stop and we showed the early phase versus a late phase video. So the question is, did the vehicle learn between the early and late parts of the project about the 4-way stop, or did you make software updates or changes to help it work later?
The vehicle did not learn. We had to do very specific updates to improve the performance from one phase to another. I would just make a general point in that the software that we used exhibited no, I would say, learning behavior. I think it was all of us that were learning, and then making very targeted updates to either the software or the map in many cases to address the challenges and the shortcomings we were seeing. And our experience has been that the map is a very good way to insert metadata for very specific locations. And you can insert metadata that helps the automation do better at just that one specific intersection and not have to worry too much about unintended consequences of changing something that now all of a sudden it doesn't work so well at another intersection. So the HD map was a good way to do that.
Okay.
I would
Go
like
ahead.
to just add something. This particular behavior at the 4-way stop, we worked a lot with autonomous stuff to try to get this behavior to act more human-like. It went through a series of changes, and I know us being able to sit in the vehicle with them and tell them exactly how we would like it to behave was very beneficial to getting the behavior to the point it's at now.
Great. Few questions that we got in during registration process was, based on these challenges, what is the most impactful adjustment that could be made with the current automation system, process, or infrastructure, which would make autonomous driving most ready for wider application? There's a second part to that question, but I'll let you answer that part first.
Yeah, I mean, there was definitely a lot of things that we observed and tried to correct. But I think one of the most impactful things that we see as being an issue is in rural areas, there's a lot of roadways that have relatively high speed limits, 55 miles an hour. And as you come up upon one of these roadways, the sensor capabilities of the automated vehicle have to be able to pick up cross traffic that's traveling at very high speeds. And our vehicle was not really initially set up to do that. And I think that this is potentially an issue everywhere, but I think given that a lot of the testing has been done in urban areas where more likely than not, cross traffic is traveling at slower city speeds, this is not an issue. But in rural areas, it is a huge issue because almost every intersection that you come up to as you are trying to get on a rural highway, the cross traffic is going to be really traveling at a very fast speed. And it may not be always like at that perfect 90-degree perpendicular angle. We saw Steve take away the first example that we worked with you today. It was actually more than that. And that certainly highlights how placement of sensors and the range of sensors can be an issue. I'm sure that my colleagues can probably think of other examples that are also would have a huge impact, and they're welcome to chime in.
Okay, if anyone, Sherry, do you want to chime in?
I was just going to say he brings up the sensors. The sensors really are the eyes. So if the sensors aren't able to detect things, it's difficult for them to be able to feed anything into the automation. So even with the dust in and the sprinklers blowing things up, and rain and snow, the weather being a factor impacts the sensors. So it's to me, the ability for the sensors and being able to see farther and in all types of road conditions and weather conditions is important.
Yeah, Sherry raises a great point about the weather. So our vehicle, maybe the audience, notice our vehicle did have a weather sensor. I mean, we had a sensor that was pointed at the pavement, so we knew what the coefficient of friction was. We knew more or less how much water and how much snow there was on the ground. But this sensor was something that we added to collect data. Unfortunately, the automation software that we used is not sophisticated enough to use this sensor or any other sensor that I know of to adjust its speed or to adjust its behavior in response to changing weather conditions. And so this is a huge issue once again for automation for four season states. When you're traveling at higher speeds in rural areas, weather plays such a huge role in what you have to be able to do in order to be able to operate a vehicle safely.
Okay. And the second part of that question that had come in was, what, if any, hard limits should be placed on any of those adjustments?
I think that's a really tough one to answer in a very generic way. I mean, I think that with these challenging scenarios that we had to deal with, when we tried to place any kind of a limit, we did it in a way that was very specific to that location. The problem with coming up with a universal limitation or a universal range that's safe, it may be applicable to one intersection or one driving area, but it may not translate well to another location and another driving area.
Okay, a couple other questions have come in. Did the vehicle operate on a fixed route, or was it able to operate on any rural roadway within a defined geofenced area?
The vehicle operated on a fixed route, and this specific type of technology that we're using, we need an HD map. And so the automation software expects an HD map, and if it doesn't have an HD map, then it will not work. So we made an HD map for a 47-mile route. We picked the roadways to be as diverse and different and representative of what a vehicle might encounter in the real world. And then we updated the HD map as needed to stay consistent, because then one of the features of an HD map is that the moment you make it, it starts to age. And so if the real world changes, you have to update the HD map. But in our experience, we did not have to do that really that often. But that could certainly change if you're in an area where they're doing a ton of construction and things are changing a lot.
Okay, next question. Did you have any lessons learned in the route design? For example, were there areas that caused particular issues that you wish you could have done more testing or more testing iterations?
I'll just provide one example, and maybe my colleagues will think of others. I think, once again, a limitation of the software is that when a route looped over itself, it caused challenges for the automation. So if we were to go into a main town area and then have essentially a go around like one city block and come back and cross over the path, then that would throw off the automation, because sometimes it wouldn't realize where it was approaching that path from, and it would try and turn in the wrong direction. And we were able to get around that limitation by breaking up our route into different chunks. But then that meant that we had to manually load different pieces of the route using the interface when we came to our natural stopping points. That was certainly one limitation.
I wanted to kind of add on to what Omar said. One of the other things that we learned, and going into it, we had the assumption that we would need other places. So we actually have not only into that 47-mile loop mapped with an HD map, but we also mapped areas around our facility. And that allowed us to actually do a lot of our local testing to take a look at these changes that we would make in Apollo. We could actually test them locally, and therefore we had kind of a nice quick turnaround on testing and making sure that things were ready to go. So that was another thing that, like, I don't think that that we necessarily put enough focus on at the very beginning. We knew that we would like to have that local route to work with. But I think over time we saw that just having more areas mapped than that specific area that we were driving helped a lot in terms of speed at which we were able to do development.
And I'll just add, so when we were designing, we had it broken up into 6 phases, how and the gravel road part was later in the study, but because it was fully mapped, we were able to at least identify very early on that the vehicle was not going to drive towards the center. So we were able to communicate with our partners to start thinking of a way to fix or address the issue that we can't drive all the way to the right in the loose gravel. So I think being able to have the full map the whole time, even though we weren't anticipating using the automation on that part, was really helpful for us to, think ahead and come up with a solution to address that issue.
Okay, that's all the questions that have come in for now. So unless we get any last minute ones, I wanted to thank everyone again for joining us. This will be recorded, or this is being recorded, and it will be available on our website, which I put into the chat for everyone. On that website, you can also find a link to our data portal, which again is publicly available. So feel free to share that. Recordings of our past webinars and other project information is also on that website. So thanks everyone for joining us, and have a good day.